a third and very popular type of generative model called GANs. So of the models that we've seen so far, pixel CNNs and RNNs defined a tractable density function, right? And they optimize the likelihood of the training data. And then VAEs, in contrast to that, now have this additional latent variable Z that they define in the generative process, right? And so having the Z has a lot of nice properties that we talked about, but they are also cause us to have this intractable density function that we can't optimize directly. And so we derive and optimize a lower bound on the likelihood instead. And so now, what if we just give up on explicitly modeling this density at all, right? And we say, well, what we want is just the ability to sample and to have nice samples from our distribution. So this is the approach that GANs take. So in GANs, we don't work with an explicit density function, but instead we're going to take a game theoretic approach, and we're going to learn to generate from our training distribution through a setup of a two-player game. And we'll talk about this in more detail. So in the GAN setup, we're saying, okay, well, what we care about is we want to be able to sample from a complex, high-dimensional training distribution, right? So if we think about, well, we want to produce samples from this distribution, there's no direct way that we can do this, right? We have this very complex distribution. We can't just take samples from here. So the solution that we're going to take is that, well, we can, however, sample from simpler distributions. For example, random noise, right? Gaussians, these we can sample from. And so what we're going to do is we're going to learn a transformation from these simple distributions directly to the training distribution that we want. So the question, what can we use to represent this kind of complex distribution? Yeah, neural network, I heard the answer. So when we want to model some kind of complex function or transformation, we use a neural network. Right, okay, so what we're going to do is we're going to take, in the GAN setup, we're going to take some input, which is a vector of some dimension that we specify of random noise, and then we're going to pass this through a generator network, and then we're going to get as output directly a sample from the training distribution. Right, so every input of random noise we want to correspond to a sample from the training distribution. And so the way we're going to train and learn this network is that we're going to look at this as a two-player game. So we have two players, a generator network, as well as an additional discriminator network that I'll show next. And our generator network is going to is player one, it's going to try and fool the discriminator by generating real-looking images. Right? And then our second player, our discriminator network, is then going to try and distinguish between real and fake images. So it wants to do as good a job as possible of trying to determine which of these images are counterfeit, are fake images generated by this generator. Okay, so what this looks like is, right, we have our random noise going to our generator network. Generator network is generating these images that we're going to call, they're fake, right, from our generator. And then we're going to also have real images that we take from our training set. And then we want the discriminator to be able to distinguish between real and fake images, right? Output real and fake for each images. So the idea is if we're able to have a very good discriminator, we want to train a good discriminator. If it can do a good job of discriminating real versus fake, and then if our generator network is able to if it's able to do well and generate fake images that can successfully fool this discriminator, then we have a good generative model, right? We're generating images that look like images from the training set. Okay, so we have these two players, and so we're going to train this jointly in a minimax game formulation, right? So this minimax objective function is what we have here. We're going to take the minimum. It's going to be minimum over theta g, our parameters of our generator network G, and maximum over parameters theta of our discriminator network D of this objective, right? These terms. And so if we look at these terms, what this is saying is, well, this first thing, expectation over data of log of D given x. This log of D of x is the discriminator output for real data x, right? This is going to be likelihood of real data being real from the data distribution P data. And then the second term here, expectation of Z drawn from P of Z, right? Z drawn from P of Z means samples from our generator network. And this term G of Z that we have here is the output of our discriminator for generated fake data, right? For our, what does the discriminator output of G of Z, which is our fake data. And so if we think about what this is trying to do, our discriminator wants to maximize this objective, right? It's a max over theta d, such that d of x is close to 1, it's close to real is high for the real data, right? And then d of g of x, what it thinks of the fake data on this left here is small. We want this to be close to 0. Right, so if we're able to maximize this, this means discriminator is doing a good job of distinguishing between real and 0, basically classifying between real and fake data. And then our generator, here we want the generator to minimize this objective such that d of g of z is close to 1. So if this d of g of z is close to 1 over here, then the 1 minus that is small, and basically we want to, if we minimize this term, then it's having discriminator think that our fake data is actually real. So it means that our generator is producing real samples. Okay, so this is the important objective of GANs to try and understand. So are there any questions about this? Yeah, so the question is this basically trying to have the first network produce real-looking images that our second network, the discriminator, cannot distinguish between them? Okay, so the question is, how do we actually label the data or do the training for this network, these networks? We'll see how to train the networks next, but in terms of like what is the data label, basically, right? This is unsupervised, so there's no data labeling. But data generated from the generator network, the fake images, have a label of basically 0 or fake. And we can take training images that are real images, and this basically has a label of 1 or real. Right? So when we have the loss function for our discriminator is using this, it's trying to output a 0 for the generator images and a 1 for the real images. So there's no external label. So the question is, the label for the generator network will be the output for the discriminator network. So the generator is not really doing classification necessarily. It is what its objective is here d of g of z. It wants this to be high, right? So given a fixed discriminator, it wants to learn the generator parameter such that this is high. So we'll take the fixed discriminator output and use that to do the backprop. Okay, so in order to train this, what we're going to do is we're going to alternate between gradient ascent on our discriminator, so trying to learn theta d, that's maximizing this objective, and then gradient descent on the generator. Right, so taking gradient descent on these parameters theta g, such that we're minimizing this objective. And here we are only taking this right part over here because that's the only part that's dependent on theta g parameters. Okay, so this is how we can train this GAN, right? We can alternate between training our discriminator and our generator in this game, each trying to fool the other. Or generator trying to fool the discriminator. But one thing that is important to note is that in practice, this generator objective, as we've just defined, actually doesn't work that well. And the reason for this is we have to look at the loss landscape, right? So if we look at the loss landscape over here for d of g of x, if we plot here 1 minus d of g of x, which is what we want to minimize for the generator, it has this shape here, right? So we want to minimize this, and it turns out the slope of this loss is actually going to be higher towards the right? High when d of g of z is closer to 1. So that means that when our generator is doing a good job of fooling the discriminator, we're going to have a high gradient, more higher gradient terms. And on the other hand, when we have bad samples, right, our generator has not learned a good job yet. It's not good at generating yet. Then this is when discriminator can easily tell it's now closer to this 0 region on the x-axis. Then here the gradient's relatively flat. And so what this actually means is that our gradient signal is dominated by a region where the sample is already pretty good, whereas we actually want it to learn a lot when the samples are bad, right? These are training examples that we want to learn from. And so in order so this basically makes it hard to learn. And so in order to improve learning, what we're going to do is define a slightly different objective function for the gradient, where now we're going to do gradient ascent instead. And so instead of minimizing the likelihood of our discriminator being correct, which is what we had earlier, now we'll kind of flip it and say, let's maximize the likelihood of our discriminator being wrong, right? And so this will produce this objective here of maximizing log of d of g of x, right? And so so now basically, we want to now maximize this flip objective instead. And what this now does is if we plot this function on the right here, then we have a high gradient signal in this region on the left where we have bad samples, and now the flatter region is to the right where we already have good samples, right? So now we're going to learn more from regions of bad samples. And so this has the same objective of fooling the discriminator, but it actually works much better in practice, and for a lot of work on GANs that are using these kind of the vanilla GAN formulation is actually using this objective. Okay, so just an aside on that is that jointly training these two networks is challenging and can be unstable, right? So as we saw here, like we're alternating between training a discriminator and training a generator. This type of alternation is, it basically it's hard to learn two networks at once, and there's also this issue of like depending on what our loss landscape looks at, this can affect our training dynamics. Right, so an active area of research still is how can we choose objectives with better loss landscapes that can help training and make it more stable. Okay, so now let's put this all together and look at the full GAN training algorithm. Right, so what we're going to do is for each iteration of training, we're going to first train the discriminator network a bit, and then train the generator network. Right, so for k-steps of training the discriminator network, we'll sample a mini batch of noise samples from our noise prior z, and then also sample a mini batch of real samples from our training data x. Right, so what we'll do is we'll pass the noise through our generator. We'll get our fake images out. So we have a mini batch of fake images and a mini batch of real images, and then we'll take a gradient step on the discriminator using this mini batch, right? Our fake and our real images, and then update our discriminator parameters, and use this and do this a certain number of iterations to train the discriminator for a bit, basically. And then after that, we'll go to our second step, which is training the generator. And so here we'll sample just a mini batch of noise samples, right? We'll pass this through our generator, and then now we want to do backprop on this to basically optimize our generator objective that we saw earlier, right? So we want to have our generator fool our discriminator as much as possible. And so we're going to alternate between these two steps of taking gradient steps for our discriminator and for the generator. And I've said 4 K steps up here for training the discriminator. And so this is kind of a topic of debate. Some people think, just having one iteration of discriminator, one step of discriminator, one step of generator is best. Some people think it's better to train the discriminator for a little bit longer before switching to the generator. There's no real clear rule, and it's something that people have found different things to work better depending on the problem. And one thing I want to point out is that there's been a lot of recent work that alleviates this problem and makes it so that you don't have to spend so much effort trying to balance how the training of these 2 networks. It'll have more stable training and give better results. And so Wasserstein-Gan is an example of a paper that was an important work towards doing this. Okay, so looking at the whole picture, we've now trained. We have this network set up. We've trained both our generator network and our discriminator network. And now, after training for generation, we can just take our generator network, and use this to generate new images. So we just take noise Z, pass this through, and generate fake images from here. Okay, and so now let's look at some generated samples from these GANs. So here's an example of trained on MNIST, and then on the right on faces. And for each of these, you can also see, just for visualization, the closest, on the right, the nearest neighbor from the training set to the column right next to it. And so you can see that we're able to generate very realistic samples, and it never directly memorizes the training set. And here are some examples from the original GAN paper on CFAR images. And these are still fairly, not such good quality yet. These were, the original work was from 2014, and so these are some older, simpler networks. And these were using kind of simple, fully connected networks. And so since that time, there's been a lot of work on improving GANs. And so one example of a work that really took a big step towards improving the quality of samples is this work from Alex Radford in iClear 2016 on adding convolutional architectures to GANs. And so in this paper, there was a whole set of guidelines on architectures for helping GANs to produce better samples. So you can look at this for more details. So this is an example of a convolutional architecture that they're using, which is going from our input Z, noise vector Z, and transforming this all the way to the output sample. And so now from this large convolutional architecture, we'll see that the samples from this model are really starting to look very good. So this is trained on a data set of bedrooms, and we can see all kinds of very realistic, fancy-looking bedrooms with windows and nightstands and other furniture around this. So it's, these are some really pretty samples, and we can also try and interpret a little bit of what these GANs are doing. So in this example here, what we can do is we can take 2 points of Z, 2 different random noise vectors, and let's just interpolate between these points. And each row across here is an interpolation from one random noise Z to another random noise vector Z. And you can see that as it's changing, it's smoothly interpolating the image as well, all the way over. And so something else that we can do is we can see that, well, let's try to analyze further what these vectors Z mean, And so we can try and do vector math on here. And so what this experiment does is it says, okay, let's take some images of samples of smiling women images, and then let's take some samples of neutral women, and then also some samples of neutral men. And so let's try and take the average of the Z vectors that produced each of these samples. And if we say, let's take this mean vector for the smiling woman, subtract the mean vector for the neutral woman, and add the mean vector for the neutral man, what do we get? And we get samples of smiling man. So we can take the Z vector produced by there, generate samples, and get samples of smiling men. And we can have another example of this, of glasses man. minus no glasses man and plus get glasses women and get women with glasses. Right, so here you can see that basically the Z has this type of interpretability that you can use this to generate some pretty cool examples. Okay, so this year, 2017, has really been the year of the GAN. There's been tons and tons of work on GANs, and it's really sort of exploded and has gotten some really cool results. So on the left here, you can see people are working on better training and generation. So we talked about improving the loss functions, more stable training, and this is able to get really nice generations here of different types of architectures. On the bottom here, really crisp high resolution faces. With GANs, you can also do, there's also been models on source to target domain transfer and conditional GANs. And so here, this is an example of source to target domain transfer where, for example, in the upper part here, we are trying to go from source domain of horses to an output domain of zebras, right? So we can take an image of horses and train a GAN such that the output is going to be the same thing, but now zebras in the same image setting as the horses, and go the other way around. We can transform apples into oranges, right? And also the other way around. We can also use this to do photo enhancement, right? So producing these really taking a standard photo and trying to make really nice, as if you had pretending that you have a really nice expensive camera, right? That you can get these nice blur effects. On the bottom here, we have scene changing, so transforming an image of Yosemite from the image in wintertime to the image in summertime. And there's really tons of applications, right? So on the right here, there's more. There's also going from a text description and having a GAN that's now conditioned on this text description and producing an image, right? So there's something here about a small bird with a pink breast and crown, and now we're going to generate images of this. And there's also examples down here of filling in edges. So given conditioned on some sketch that we have, can we fill in what a color version of this would look like? Can we take a Google, a map grid and put something that looks like Google Earth on and turn it into something that looks like Google Earth, right? Fill in and hallucinate all of these buildings and trees and so on. And so there's lots of really cool examples of this. And there's also this website for Pix2Pix, which did a lot of these kind of conditional GAN type examples that I encourage you to go look at for more interesting applications that people have done with GANs. And in terms of research papers, there's a huge number of papers about GANs this year now. There's a website called the GAN Zoo that kind of is trying to compile a whole list of these. And so here you can see this is only taking me from, A through C on the left here and through L on the right. So it won't even fit on this slide. There's tons of papers as well that you can look at if you're interested. And then one last pointer is also for tips and tricks for training GANs. Here's a nice little website that has some pointers if you're trying to train these GANs in practice. Okay, so summary of GANs. GANs don't work with an explicit density function, right? Instead, we're going to represent this implicitly through samples. And they take a game theoretic approach to training. So we're going to learn to generate from our training distribution through a two-player game setup. And the pros of GANs are that they're really having gorgeous state-of-the-art samples, and you can do a lot with these. The cons are that they are trickier and more unstable to train. We're not just directly optimizing this a one objective function that we can just do backprop and train easily. Instead, we have these two networks that we're trying to balance training with, so it can be more unstable. And we also can't lose out on not being able to do some of the inference queries, right? P of x, P of z given x that we had, for example, in our VAE. And GANs are still an active area of research. This This is a very relatively new type of model that we're starting to see a lot of, and you'll be seeing a lot more of. And so people are still working now on better loss functions, more stable training. So Wasserstein GAN, for those of you who are interested, is basically an improvement in this direction that now a lot of people are also using and basing models off of. There's also other works like Ellis GAN, least squares GAN, and others. So you can look into this more. And a lot of times for these new models, in terms of actually implementing this, they're not necessarily big changes. There are different loss functions that you can change a little bit and get like a big improvement in training. And so this is some of these are worth looking into, and you'll also get some practice on your homework assignment. And there's also a lot of work on different types of conditional GANs and GANs for all kinds of different problem setups and applications. Okay, so a recap of today. We talked about generative models. We talked about 3 of the most common kinds of generative models that people are using and doing research on today. So we talked first about PixelRNN and PixelCNN, which is an explicit density model. It optimizes the exact likelihood, and it produces good samples, but it's pretty inefficient because of the sequential generation. We looked at VAEs, which optimizes a variational or lower bound on the likelihood. And this also produces useful latent representation. You can do inference queries, but the sample quality is still not the best. So even though it has a lot of promise, it's still a very active area of research and has a lot of open problems. And then GANs, we talked about is a game theoretic approach for training, and it's what currently achieves the best state-of-the-art examples. But it can also be tricky and unstable to train, and loses out a bit on the inference queries. And so what you'll also see is a lot of recent work on combinations of these kinds of models, right? So, for example, adversarial autoencoders. So something like a VAE trained with an additional adversarial loss on top, which improves the sample quality. There's also things like, Pixel VAE is now a combination of Pixel CNN and then VAE. So there's a lot of combinations, basically trying to take the best of all these worlds and put them together. Okay, so today we talked about generative models, and next time we'll talk about reinforcement learning. Thanks.